One more work energy theorem problem, and then we'll move on to talk about something slightly different. Remember, I told you we could also use potential energy. We've been talking about problems that involve kinetic energy so far. So in this one, we have a climber, a mountain climber. 65 kilograms is her mass. How much work does she do when she climbs from an elevation of 1,500 meters to 2,000 meters? These both are heights. When you see a height, you should be thinking potential energy. When there's speeds, it's kinetic energy. When it's height, it's potential energy. This is our initial height. This is our final height. All right. So again, here's where she is. I'm assuming she's already come up from the ground. So this is the initial energy state. This is the final energy state. We're looking at potential energy both places. We have her height in both places, not concerned really about her speed at this point, just concerned about the height. How much work does she do? Again, we're going to do EF minus EI equals FD, put the whole thing in there, and then we're going to decide which one we don't need. On this one, you could go one of two directions. Someone might be able to say, well, we could use force times distance because we know that she's lifting herself up the mountain, and I know the force that she's going to use is equal to her weight, so we could calculate this and we could put that weight in there. Yeah, technically you'd be correct. And then the distance, basically the distance you have to find is the difference between these two distances, and I don't want to mess with that. You guys don't want to mess with that either. So here's the deal. Let's just go with this. They don't give you her force, and they sort of give a distance, and you could find it, but I think it's a little bit easier to just go with EF minus EI because we know both of them are potential energy. We know the equation for potential energy so that we can put that into each one of these. Each one is going to be mgh. She has potential energy in both places, right? And this will be her final height. We just said that, and her initial height. So let's just plug numbers into this. Again, I think it's conceptually a little easier to do it this way. Her mass is 65, G is 9.8, and her final height was 2,000, right? And we would need to do this separately. We need to get a number for all of that. Again, mass 65, G 9.8, and her initial height 1,500. We need to do all that and get a number for that, right? So if you calculate all this and all this, you should get this. 65 times 9.8 times 2,000 will give you this number, 1,274,000. That's the potential energy she had at the end. And we're going to subtract that from her initial potential energy, which is, if you multiply 65 times 9.8 times 1,500, you get 955,500. That's the number there. All right. And now all that's left to do is simply subtract those two, and you would get 318,500 joules. That was her change in energy from 1,500 to 2,000 meters. Therefore, since that's her change in energy, that's how much work she did, 318,500 joules. Again, you could do this with FD, but you would have to first of all find her weight to figure out the force. And then with the distance, you would simply have to know that the distance she climbs, the total distance she climbed there from 1,500 to 2,000 meters was a total distance of 500 meters because that's the difference between those two. So 2,000 minus 1,500 would be a distance of 500. You could do that and you would get the same answer. You would get the same answer if you did that. And if that makes sense to you, then do it that way. But in my opinion, to me, it makes more sense to just calculate her potential energy, subtract the two here, and you get your answer.